Students, now let us study preparation of ethers. We will study two of its methods of preparation which are included in our syllabus. First of which is something which we have taken up in our last reactions of alcohol. We know that the alcohols undergo dehydration in presence of protic acids like sulfuric acid at 443 Kelvin to give us alkene as our product. That is, over here we find ethanol giving us ethene as our product. But the same alcohol undergoes a reaction with your sulfuric acid, that is a protic acid over here, but at a slightly lower temperature of 413 Kelvin and ends up giving us a ether as a product. Okay. Of course, if you go to see the two sides of this reaction, that is the reactant and the product, the reaction is not balanced. Okay, because for the formation of this ether, we require 2 moles of this alcohols to react in order to give us the product. But what we understand from this is that the alcohol can also undergo nucleophilic reaction. So here the reaction which is undergone is nucleophilic substitution reaction, which is following the SN2 path bimolecular to give us ether as our product. Okay, so here there are two possibilities. The same reactant can undergo elimination reaction also, and the same reactant undergoes SN2, that is nucleophilic substitution bimolecular reaction to give us ether as our product. So this is our first method in the preparation of ethers. Let us understand the mechanism. The mechanism goes very simple. I have ethanol. Ethanol undergoes protonation. The proton comes from the acid, thus giving us protonated alcohol. So this is our protonated alcohol. This protonated alcohol is attacked by another molecule of alcohol. Look at it. Now this one acts as a nucleophile and this is becoming an electron deficient species. So you have lone pair of electrons on oxygen which goes to attack a carbon over here. Thus water molecule is lost. Okay. So losing a water molecule, what you obtain is a protonated ether. This is protonated ether. What will be our next step? Yes, correct. To obtain an ether, I just have to get rid of this hydrogen. So that is lost over here as a hydrogen ion, giving us ether as our product. So that is obtaining a ether from a protonated ether by a deprotonation process. So if you go to see, understand the mechanism over here, we find that in the first method of preparation of our ethers, we follow the method of nucleophilic substitution reaction undergone by two molecules of alcohol at 413 Kelvin in presence of a protic acid like sulfuric acid over here, and the mechanism which is involved is first protonation, second attack of an alcohol on a protonated alcohol, and third one is deprotonation of the protonated ether. In this case, we have to understand that this particular method is very much suitable for preparation of ethers which involves the primary alcohol. If we have secondary and a tertiary groups involved over here, this method may not be a suitable method for preparation, because there is every possibility, rather than undergoing a nucleophilic substitution reaction, it will undergo elimination reaction to form alkene as the product. Let us continue studying the second method in the preparation of ethers, and that is Williamson synthesis. Now, what is this Williamson synthesis? It's very simple. We have a alkyl halide which goes to react with sodium alkoxide, thus giving us ether as our product. So look at it. The alkoxide part comes from the sodium alkoxide, and other alkyl group is being provided by alkyl halides, thus giving us sodium halide as the byproduct in the reaction. We have another example over here. Now look at it. This is a tertiary group. So this one is sodium tertiary butoxide. So this one is the compound which we are having, goes to react with methyl bromide. I am using a common nomenclature over here, methyl bromide, thus giving us ether as our product. Look at it. In this particular case, I am having the tertiary part coming from the sodium alkoxide part, and the primary group over here is coming from the alkyl halide part, thus giving us ether as our product. But if, say, suppose a simple question can be asked, can I interchange this? That is, can I have a tertiary group being attached to a or it can be a alkyl halide, and the primary one to be the alkoxide part, whether the same reaction will be undergone? No. Over here, you need to have the alkoxide part which is there, can be primary, secondary, or that of tertiary, but the alkyl halide part has to be always primary. If you are intending to take it as secondary or that of tertiary, there is every possibility that it will undergo elimination reaction and you are going to obtain alkene as your product. The same is being shown over here. Look at it. As we have as we have taken the case over here, if I am having this tertiary butyl bromide and I am having sodium methoxide, here is the thing, it is undergoing elimination reaction. So your bromine is the bromine is removed along with the sodium, and sodium bromide is formed. Your CH3O and H from here goes to give you CH3OH, and what you obtain is alkene as your product. So you have to understand over here that when we want the Williamson synthesis to be undergone, Williamson synthesis is nothing but a reaction of sodium alkoxide with that of alkyl halide. The alkyl halide has to be always primary. If it is secondary or that of tertiary, it will tend to undergo elimination reaction, giving us alkene as our product. Let's continue. If I have to go for a preparation of aryl ethers, in that case, Williamson synthesis again is a very good method. So I have phenol which goes to react with sodium hydroxide. This reaction we have seen earlier, thus goes to give you sodium phenoxide. Sodium phenoxide reacts with alkyl halide, and thus oxygen of your sodium phenoxide attacks the alkyl part, and sodium goes along with halogen over here to give you sodium halide and your main product, and that is your aryl ether.